Lecture 17 covers Section 5.6. At the end of today's lecture, you should be able to construct an expression that relates the maximum power transferred, i.e. P sub max, by a circuit to a load resistance. To begin, let us consider the circuit on the left. Say we have an arbitrary circuit A that is connected to a load resistance via terminals A and B. We want to choose R sub L that would maximize the power output of our circuit. What we could do is vary values of R sub L and track the current running through it, and then look for the maximum. Or, if we know our open circuit voltage and short circuit current of circuit A, we can determine a proper quantity for our Thevenin resistance and relate that to our load resistance such that we can maximize the power of our circuit. Conversely, if we look at the circuit on the right and we are given a load resistance, we can specify our open circuit voltage source and our Thevenin resistance such that we maximize the power transferred to our load resistance. Now, if we recall our expression for power, power is equal to I squared times R sub L, where I is the current running through our circuit. Now, I, expressed in terms of our open circuit voltage, Thevenin resistance and load resistance, is simply our open circuit voltage per the sum of our Thevenin and load resistances. Now, that leaves us with the following expression. Our power dissipated by our load resistance is equal to our open circuit voltage per the sum of our Thevenin and load resistances, this quantity squared, times our load resistance. For us to mathematically determine the values of our Thevenin and load resistances that maximize power output, we proceed with the following. To maximize any expression, we take the derivative of that expression with respect to our variable of interest and set it equal to 0. This will give us a local maximum. You can ensure that this maximum is the global maximum by taking the second derivative and setting it equal to 0. So what we're going to do is differentiate power with respect to load resistance. That is, we have the derivative of power with respect to RL. We will make the substitution of power as a quantity VOC per R Thevenin plus RL squared times RL. And we will differentiate this with respect to RL and set it equal to 0. In doing such, we're going to have to apply the quotient rule and product rule. That is, when we take the derivative of power, we'd have the following. We'd have our Thevenin plus load resistance quantity squared times our open circuit voltage squared minus 2 times our open circuit voltage squared times our load resistance times the quantity our Thevenin plus load resistance per the quantity of our Thevenin plus our load resistance to the fourth. And we set this equal to 0. If we multiply by our Thevenin and load resistance to the fourth and divide out by our open circuit voltage squared, we'd be left with the following, where we have our Thevenin plus load resistance quantity squared minus 2 times the load resistance times the quantity our Thevenin plus load resistance, and set this equal to 0. If we expand out the first term within our expression and cancel out like quantities, we would have the following. Our Thevenin resistance would be equal to our load resistance. Or conversely, the load resistance would be equal to the Thevenin resistance of our circuit, such that this quantity maximizes our power output. Now, if we want to express our maximum power output in terms of our open circuit voltage, our short circuit current, and our Thevenin resistance, we'd have the following. If we go back to our original expression of our maximum power, which was expressed as our open circuit voltage per our Thevenin plus load resistance, quantity squared times our load resistance, and make the substitution for our Thevenin to be equal to RL, we would have our maximum power being 1/4 times the quantity of our open circuit voltage squared per our Thevenin resistance. Or substituting in terms of I, our maximum power transferred would be our Thevenin resistance times our short circuit current squared per 4.